Hello, welcome to Hyfindr Tech Talks. My name is Steven. Here we look at the technology that makes the hydrogen economy work, and today we are going to go deeper into fuel cell systems, optimizing them and around the balance of plant and everything. For that, I have an expert who has been here before. I'm very grateful that he took the time to come back. He works for AE Driven, a system integrator, and I'd like to welcome Christoph Ley.
Thank you, Steven. Hi.
Christoph, it's great to have you here again. And last time you took us from the cell to putting a whole system together. We see that here, the whole architecture with the anode and cathode side. Today we want to talk about how we're going to get the most performance out of this. So maybe you can just, do you want to start with the diagram and give us a few hints?
Yeah, I'll start with the diagram. So let's have a look at the different system in a fuel cell system. So we have the anode system, we have the cathode system, and we have the cooling system. And now the question is, what can we change here? What can we improve to get more power out of it, to increase the efficiency or something like this? So let's start with the cathode system. So, in example, this is one very important part, a very important part. This is a fuel cell compressor.
Ah, this is a compressor, okay.
So one example.
So this supplies the air into the stack.
Exactly. So when we look at the PNID, we start with the dry air inlet go through the filter and then in the compressor. Okay. So from the compressor through different components into the cathode side. So this component transport one of the reactants that are absolutely necessary to get the power out of the fuel cell stack. So the question is, what would be if we take a bigger compressor or a smaller compressor, and what is the impact from the compressor or of the compressor for the efficiency and so on?
Okay, maybe just one basic question coming back to the system. How does this work? So if I blow more air in here, then I just get more energy out, or how does it work? Is it the more I blow in, the more I get energy out?
So you can do it in some in a special range. Yeah. So you can increase the pressure on the anode side, on the anode side, so putting more hydrogen into the fuel cell, and on the cathode side also putting more oxygen that comes out of the air.
So that's what the compressor is pushing.
Exactly. Okay. The pressure on the anode side is a little bit more bigger, and so special range because there is this membrane inside of this stack, and we don't want to damage it. So because that is why there's a limit for the pressure. Okay. Exactly.
But just to ask the basic, really simple question: if I have a stack here and it's the thing is running, and I want more power out of that, what do I actually need to do? I need to increase the flow on both sides, and then it just happens.
You increase the flow on both sides, so these processes must be controlled. So also, as mentioned, to avoid damages and so on. But the result would be that there is a higher power generation inside of the stack.
Yeah, okay.
But this is just the gross power. So let's go to the next slides, and then we talk about gross power and net power. So at first, there's always the question, what is the power demand? So what power or how much power should be generated by the fuel cell system and provided to, in example, when we're talking about a vehicle application, provided to the drivetrain of the vehicle. Or if we're talking about a stationary application.
Can I take this away?
Yeah, for sure.
Okay.
For sure.
Go on.
So when we look here, we've got a load profile.
Yes.
And there we can see, okay, here are some peaks and so on. So how to provide the power for these peaks? Yeah. There are different principles to do this. So you can, you can combine a fuel cell system with a battery system, with a high voltage battery system. So that means you run the fuel cell more in a kind of static operation mode or operating mode, and the dynamic things like these peaks are supplied by the high voltage battery. So you can do it like this. So the benefit of this is you can run the fuel cell system on a very efficient point. So, as mentioned before, you can increase the pressure on both sides, on the anode side and also on the cathode side. Yeah. But when you increase it on the cathode side, you also need more power for the compressor. So, and this power is provided by the fuel cell itself. So, and then there's the question, does it make sense? So, okay, here is the other alternative, so to run it more in this dynamic operation mode, operating mode. So that means we have a bigger fuel cell system and we run it nearly on full load. So then we have a small battery. So the main provider of the energy that is used by the application is provided by the fuel cell.
Okay.
So that means we try to use the whole pressure range for the fuel cell, but that also means when we use higher pressure, the efficiency would go down. Exactly. Okay. Perhaps we can see it on the next slide.
Yes.
So on the left side, you see the gross efficiency.
So gross efficiency means essentially the efficiency of the stack only. And when you say net efficiency, that means the efficiency when now you consider the compressor, which is this one, and some other components which may also be there. Yeah. Okay.
Exactly.
So you've taken away the own consumers, basically.
Exactly. So for the application, the gross efficiency is not so important. So you can see here different curves. You can run the system nearly in ambient mode, so with low pressure, to call it like this, but you can also increase the pressure up to 2.5 bars. Exactly.
On the air side, on the
on the on the air side. So that means also you can see it here on these curves. There's more power generated in the stack, but there are not only benefits. So more power seems to be a benefit, but when we look at the right side, so for the netto efficiency, the output power, the netto output power, and that is what is important for the application.
Zoom that a bit. Yeah.
That goes down, and that is because when we run the system at 2.5 bars, we need a very huge compressor, and the energy consumption of this compressor would be very high. And let's also think about other components. In example, about the cooling pump. So
the coolant, so ionized water, or what is it that you use?
Exactly. So the coolant pump is used for transporting the coolant medium through the stack, take the heat out of the stack, and through it away with other components and so on.
So the more you have to cool, the more this guy has to run.
Exactly. Exactly. And perhaps it must be bigger. And so on. And when you look at the cooling area that you need for these higher power levels, so there is more power generated by the fuel cell itself.
Yes.
So, and when we're talking, in example, about 50% efficiency or other values or other numbers, the rest is heat. So more heat needs to be transported away.
Understood.
Exactly.
So that means when we look at this curve here, so you said when you have the system running at almost ambient condition at 1 bar, when we're running on low output performance, we're nice and high with the efficiency, but that drops quickly as we increase the output power.
Exactly. Yeah? So this is the question that we have for designing the balance of plant. So we want to find a very efficient point. So to run the system efficiently, and then we say, okay, we need this compressor, this coolant pump, and so on. So that means at the beginning, for sure, you can say, okay, I want to run the system at 1 bar, in example, but for a special area here in this field, that is absolutely okay. So when you go when you would take out a little bit more than 20 kilowatt, okay. So, but when you want to have more than 25 kilowatt, you can see here it drops down.
So when you want to run at, for example, 30, then you're better off taking a system that runs at a higher pressure.
Exactly.
Because the 1 bar system would hardly make it there.
Exactly. Yeah. So, and then when we think back about
It takes a while.
Doesn't matter about the exactly here about the load profile.
Yes.
So just imagine this is a 30 kilowatt peak, an example.
Yes.
So then you can supply these 30 kilowatt peak perhaps on a different pressure mode. So with higher pressure you can supply the power for this. But perhaps it would also make sense, so when you see the whole energy system or energy management system, perhaps it would also make sense to combine a perhaps smaller fuel cell system to run it very efficient on 1 bar or 1.5 bar and to supply these peaks by a battery.
Okay. So yeah, is there more to it than this? I think you mentioned about the different gross output powers here and the DC-DC conversion.
Exactly. So here is the energy consumption and hydrogen consumption. So here in this diagram you can see when we run the system at 2.5 bar, the main consumer of the generated power is the compressor. So this kind of blue area here. Yes. So there are other components like the DC-DC. So there's a conversion in it. So there are also some losses and so on, but these are not so high. So the statement out of this graphic is the compressor on this high operating point, so with 2.5 bars, is the main consumer here. And also when you look at the hydrogen consumption, so you compare the efficiency with the hydrogen consumption, you can say, okay, to get more power out of the system, net power out of the system, you need much more hydrogen and the efficiency goes down.
Okay, so what you're saying is I first need to look at what my demand is and then also what kind of operating modes are most likely. So let's say I have a system that needs a constant supply of say 200 kilowatt. How would I then go about optimizing my little system or whatever I have to get to that point where I'll say, okay, this is the best in terms of efficiency and performance?
So when you say that the system should supply continuously 200 kilowatts.
Yes.
Continuously.
So I'm in the desert and I want lighting for my film set. Yes.
Okay, then you would take design a fuel cell system that is optimized for a very efficient operating point at this 200 kilowatt. So to call it in numbers, you would not take a 200 kilowatt fuel cell system because that would mean it provides 200 kilowatt at full load, but you don't want to have full load because that is the most inefficient point that you can get.
Is it?
Exactly. So that means you need a bigger system. Or you could combine two smaller systems to provide in total these 200 kilowatt continuously.
Okay, understood. Okay, so that's some of the play. Is there more to know in terms of when you are really now like in the mode of tuning, get the most out of your system?
To get the most out of your system. So let's have a look at this slide here. So when you have a power demand, also power demand 80 kilowatt. So what are the KPIs or the numbers that we're talking about? We're always talking about efficiency, we're talking about lifetime and we're talking about TCO. So, and again, this comparison, big fuel cell system with a small battery system, and this system is running perhaps not on full load, but in the near of full load. So the efficiency would be very low, but also the lifetime would be very low. So, and when you think about the TCO, not only because of the operating cost itself, so for hydrogen consumption and so on, also for the lifetime of the system. So you don't want to...
TCO means the total cost of ownership of the entire system or just the fuel cell system?
The entire system.
The entire system.
Of the entire system, but the critical part here is the fuel cell.
Okay, understood.
Exactly. So because of the single cells and the membrane and so on, and when you run it always on high pressure and so on, so then there is so the mechanic forces on these components are very high and so on. So that is not what we want to have, because you don't want to throw the system away after 5 or 6 years. It's much better to run it 10 years or 12 years and so on.
Okay, so just a few nuggets out of that. So that means you're saying if we run high pressure on both the hydrogen and the air side, let me just call it that, the anode and cathode, then we can get more performance, more power out of the system, but we reduce lifetime.
You reduce lifetime and you increase the operating cost because you need more hydrogen.
So that means the efficiency goes down.
Exactly.
Okay. So what am I best of doing? I'm best of buying a big system and then operating that at less, so 70%. Of its peak performance, or
so in part load, operating a fuel cell system in this part load area makes more sense, because there's the efficiency very high, and also this degradation effects on the fuel cell itself are not so big. So, or the other thing is that you combine two smaller fuel cell systems. So, an example that is here on the right side, you see here this average energy demand 80 kilowatt. You say, okay, you take two smaller systems, so not 80 kilowatt. You say you take two 60 kilowatt systems, and one system runs continuously. So an example for 30,000 hours, and you activate the second system, here in this case for 10,000 hours, and all in all you have a better lifetime and lower hydrogen consumption.
This is a nice example to see that you actually can put two systems instead of one.
Absolutely.
I mean, obviously then, in terms of cost, that has to be optimal. But Christoph, let me use the opportunity to try and tickle some numbers out for you. So when you say running a system in part mode, that means if we're talking about two systems for 60 kilowatt here now, that means these are systems that can do maximum of 100 kilowatt, and then I'm just running them at 60% all the time. What's like a nice sweet spot for running the thing more or less forever?
So an optimized system for 60 kilowatt would be at 80 or 90 kilowatt.
Peak power.
Exactly, exactly. So exactly. So you run it on a lower operating point where the efficiency is very high. Okay, it depends a little bit also on the characteristics of the stack. So there are differences between the different suppliers. Yes, for sure. And you have to think about this. But so in the near of these numbers,
is there actually harm if I run it even lower? Maybe it's not optimum, but would the system be happy to do 30 kilowatt as well for the same amount of time as the 60? So what I'm saying is, does it improve other things if I run it even lower than the 60 kilowatt?
Yeah, for sure. As mentioned, the efficiency would be high. Hydrogen consumption would be very low, but also the forces and so on the other system components. And also when you run it continuously on this low operating point, you have to think about, okay, if I don't need to supply the power for these peaks, so I do it otherwise with a second system, with a battery or whatever. So perhaps I don't need such a big compressor.
Okay, then you can take a smaller one.
And also when we're talking again about the compressors, I know this is not about compressors here at this talk, but taking a compressor that can charge up the cathode side up to 2.5 bars, is it really able to perform also very efficient in a lower pressure range? So an example at ambient mode. So, and I would say no.
So that means designing or optimizing a fuel cell system is as much about, let me say, finding good conditions for the stack as is about finding the right components around and finding a compressor that will run efficiently in different kinds of zones.
Exactly, and we're always talking about this compressor or about a compressor because this is absolutely the main consumer in the system.
Is it? Even more than the cooling and all those other things. Okay.
Exactly. So also in its cooling demands, as mentioned. So when you have one single system, you run it at a very high point, so on full load, you need so much cooling area. And when you think about a truck, an example, so where to place all these radiators and so on. So the efforts for this are very high.
Okay. Well, there we see that actually there's a lot of variables that go into optimizing such a system. I thank you, Christoph, for taking us through this path, at least in its rudimentary form. I think this has been very good. Thank you very much. I feel we should talk more. Maybe we should do that at some other occasion. In any case, I want to thank you very much for watching. Thank you very much, Christoph, for coming, for sharing this with us. If you want to find components that you can use to optimize the system, you can go on Hyfindr. But actually on Hyfindr, you also find contact to Christoph, who does system integration and whose specialty is actually the optimization of such systems. So looking forward to people speaking more with you about this. If you like this video, please subscribe or give us a positive note somewhere, or just come and watch another one. Thank you very much for watching. Thank you very much for your time, and have a lovely day.
Thank you.
Bye.